Welcome to podcast number 44. Uh, we're getting up there. So this is the last of the Alkynes ones. Just again, just like before, just going down the path of doing reaction after reaction. Big thing at the end of this one, and something that hopefully you've caught on to, and it really has proved helpful, is making a summary chart of all your reactions. Now, again, called a spider chart in some cases, or a clock chart. Whatever you want to call it, just listing all the different reactions you can do. It's a great summary. So let's tie off the last few reactions. And again, most of these you probably will recognize right away because you did them on alkenes, but still take the time to notice the nuances, the subtle differences between how they work with a double bond and how they work with a triple bond. But one of the things we did with alkenes, we added HBr or HCl or HI in some cases. We added across the double bond, but this one does something differently with alkynes. For whatever reason, the density doesn't work well when we protonate, or electron density situation doesn't work well when we protonate an alkyne to generate a vinyl carbocation. It doesn't work that way. So it has to do something a little bit differently. So whereas it was similar in the previous reactions, this one's going to do something just a little bit odd. So the HX doesn't add H plus and a BR, or H plus and X minus. Instead, it forms this weird sort of aligned transition complex. So two HXs align in a way where BR is near one carbon, so it's near the pi bond. So the p orbital, let's say, is right here for one of the pi bonds. Then this BR can overlap here. And then let's say the rest of that pi bond is here, can overlap with the H accordingly. So similar to the orbital alignment in an E2 elimination, this is almost like the reverse of that, where the orbitals are lined up in a certain way, where instead of it going away, they're forming this with a pi bond. And get rid of my orbital picture and drawing that it does something like this. So this is arrow pushing to try as best we can to describe what's going on, but electrons in this bond, HBr is a strong acid, so the electrons go to Br, now becomes negative, so those electrons can swoop into this carbon right here. Once it does that, those electrons will now be pushed over and become a negative on a carbon, which can take an H, which knocks electrons back to Br. We have a Br minus. So in the end, we're going to, with an H plus and a Br minus, as expected, we're also going to add a Br and an H. Now note that it adds the Br to the more substituted and H to the less substituted side. If it was symmetric, wouldn't be a big deal, but because it's not, we're actually sending Br to the more substituted. So there must be something to do with a delta plus on this carbon more so than this one in some sort of resonance intermediate. So this mechanism, not going to test it because it is not fully understood, but I do know this much. This is partially positive, which makes this partially negative, partially positive, partially negative, partially positive, and partially negative. So this alignment of charges kind of explains how it forms this species. In the end, when everything's said and done, we will have an H plus down here. And we will have a Br minus up here. And so one of the HBRs adds across the double bond, or triple bond, leaving a double bond, and the other one is set to the side. So a second equivalent can go on. So if you add too much HX, then you can actually add on to here and protonate. And as it were, you can protonate here, that comes over that way. This can stabilize it with some resonance. And then you get the dihaloalkane. So you get two BRs on that same carbon. But that's just extra little, oh, by the way. But the one thing to make note, it does not go through this pathway that we would have probably originally predicted, where the pi bond goes and picks up the H, leaving a carbocation on the more substituted carbon. Problem is that's a vinylic. And so the problem with this drawing is that actually it would look like this because it's in a dp orbital. You do not get this species. It is not stabilized by that enough by that R group. So vinyl plus charge won't happen. Okay, so that's one reaction. Let me get rid of my writing because I just put it right in the way of everything else. So vinylic carbocation is too unstable to form. Okay, next on the agenda. Halogenation of alkyne. So halogenation meaning we add not an H in a halogen, but two halogens. Br2 and Cl2 are our usual candidates. Note that this one has no stereospecificity anymore. It can add either trans or cis. I'm going to most often write trans just because I want to stay in tune with what I do with alkanes or alkene chloroalkanes, but it's not, it's just habit more than the way it actually works. So you get both geometrical isomers. When you had more Cl2, then you can keep on adding across this double bond. Notice that you get dichloro at both sides. Not a surprise, we saw that with bromination as well. So just halogenation works this way. And in future chapters, when we start looking more at halogens, we'll go into why we usually brominate and fluorinate. But long story short, fluorine is usually too reactive, iodine's not reactive enough, and Cl and Br are just about perfect. Last reaction to throw at you, ozonolysis. Again, we went in pretty good detail in the mechanism in alkenes, so I'm going to ignore the mechanism here and just focus on the end result. So if you recall, ozonolysis will break a double bond, well, also breaks a triple bond. Breaks all three bonds, so you now have 1, 2, 3 bonds that have to be bonded to O. So I'm going to redraw this, going to take this segment, move it over, take this segment, move it over. And because we can't have a triple bond to O, I'm going to make 1, 2, 3 bonds this way, 1, 2, 3 bonds this way. So where it's broken, I'm going to put O's on the other side. Now these O's end up as OHs because you have to have 2 bonds to oxygen, so 4 bonds total, 1, 2 with H, 3 and 4. Here, 1, 2, 3, 4 bonds between the O's, so 2 to each. So you end up getting carboxylic acids. Really don't even need much in terms of the workup. So I'm going to get an O from there and an OH from the water and going to balance it out. So let's see what I've done. I've added 1, 2, 3 O's plus OHH, so 1 water. So the atoms work up exactly. Don't even need a reagent to carry this out. The water just cleaves it. So hopefully this is pretty straightforward. Again, just like alkenes, it's cleaving a carbon-carbon connection. So double bond in one case, triple bond in the other, but it works beautifully. So we've done all this. We've done all the reactions, the mechanisms for alkynes. I don't plan on making as big a deal about them on tests, but if you know it really well for alkenes, you can figure it out for alkynes as well. What is critical is dealing with the large amount of information that we're now getting in terms of reactions. So what you need to do is be able to look at a reaction and make a prediction of what has happened, or recognition of what's happened and a prediction of how to carry it out. So name that reagent that carries out each of these steps. So I start with a terminal alkyne. I have a terminal alkene, so I know I didn't deprotonate. And I've added a Br on the more substituted and H on the less substituted. So if I pay attention to what have I added, I'm going to put this H in here. And trans or cis is again irrelevant because it's not a geometrical isomer, doesn't limit it. In fact, I've changed my mind. I'm going to draw it cis so I don't get in the way of what I've drawn there. So H and Br have been added across. The Br went to the more substituted carbon. So it's not Markovnikov because it's not a double bond, but it's Markovnikov-esque, which means I just simply add HBr. So HBr adds across the alkene and the alkane both. So alkene and alkyne both, excuse me. Okay, that wasn't bad. This one, so I noticed this part has stayed intact, triple bond, but the H is replaced by CH3. This is one of those that, again, you've learned in SN2 chemistry, but if we can make this alkyne, excuse me, shoot, I've done this video after video, so sorry. But if I deprotonate this and make it a great nucleophile, put a negative charge on this carbon with a lone pair, it can attack a CH3 that has a good leaving group. So we're going to deprotonate it first, And second, we're going to do an SN2 reaction because it's a great nucleophile with a CH3X. And X has to be a good leaving group. So I could put CH3Br, CH3I, CH3Cl, whatever I put in there. But the first thing I'm going to do, use an amide to deprotonate it. I could also use LDA or butyl lithium. Deprotonate it, add the R group. Next on the agenda, we have a carbonyl. So I need to, when I see something like this, decide, did the number of carbons change? If it changed, we probably did ozonolysis. With a triple bond, it would have been an alcohol or OH there, so it would have been a carboxylic acid. So that should be one data giveaway. And the other thing is 6, 1 and 2. So 6-member ring, 1 and 2. We didn't get any carbons, so we added an O. The O went to the more substituted side, whereas over here, it got an H and an H. So we gained water in an anti-Markovnikov-like fashion. Going back to what I did in alkene chemistry, we added BH3. Again, because of the fact that this is linear, the bulkiness limitations aren't as much. So we use a slightly bigger reagent here. We use 9-BBN or some variation on that. So we added O anti-Markovnikov, and it went through an enol, if you recall. And then the enol tautomerizes into the aldehyde. So the reagents we need are 9-BBN. That's what I'm going to use. So any bulky boron hydrogen delivering system. And then peroxide workup. Okay, so doing pretty good. And guess what? 3 more. So now I'm doing internal alkynes. So I want to make sure I understand that sometimes what a terminal alkyne does, an internal may or may not do. But taking that one compound we made in a previous step where we took off the H, made a nucleophile and added CH3X to add a CH3 group to the chain. I go from here to here. Everything stayed the same except double bond, which means I hydrogenated. If these are here and here, that means the H's are respectively up and down. Those are trans H's. So if they're anti-addition of hydrogen, I know we need the sodium ammonia combination. So sodium metal and ammonia liquid. But if we atom syn, so the 2 groups are down, which means the H's are up. So let's put the H's in. Note that the H's are now syn, so syn addition of H2. And we need H2 and Lindlar's catalyst. We need that poison in there to stop it. And lastly, I have a carbonyl again, so I have to think first and foremost, was it potentially a cleavage with ozonolysis? If it were, I'd have 2 species. I'd have a carboxylic acid here. I don't have carboxylic acid, and total number of carbons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it wasn't a cleaving of a bond, so it wasn't ozonolysis. It had to be addition. So just like we looked at the one where the aldehyde formed previously, now I'm going to look at this one and show that the carbonyl is there. And again, you're getting H's here and here. So when that happens, when it's O one side, 2 H's on the other, I know that I had an OH and an H, and then I move an H over through tautomerization. So it has to go through an enol intermediate. So I'm adding O to the pi bond in the form of an enol at first, which tautomerizes to form a ketone. So sodium borohydride was what I would use, borohydride, BH3, I would add normally, or some variation of that boron species. This time, I'm going to add the mercury species, same one that ends up getting us Markovnikov addition for an alkene. So mercury in conjunction with water and strong acid will put on a enol here, double bond will be here and OH here, and then would tautomerize into the ketone. So it really comes down to recognizing what has changed and then making some sort of, I guess, organized list of reactions. Speaking of that organized list, again, recommending a clock chart, a spider chart, whatever you call these things. Start with a reagent. So I'm going to start first off with a terminal alkyne, and then I'm going to add whatever reagent I need to carry this out. So if I were to add butyl lithium with the CH3Br, butyl lithium will deprotonate, this nucleophile will come in, attack, and I end up with an internal alkyne instead of a terminal alkyne. I want to put both. I'm going to do my spider chart a little bit differently. I'm going to have one overall reaction in the middle, and then I'm going to show reactions of this species and reactions of this species. And I want to be sure that that I know whether it only reacts with a terminal, only reacts with an internal, or can do both. So for instance, H2 and Lindlar's catalyst, I know we found that it could do any type of alkyne. So I could add it here. I could also add it here. So I want to just make that little note, can go with either internal or terminal. Okay. If I didn't have the poison, if I didn't use Lindlar's catalyst, then it would reduce it down all the way to the alkane. Add H and H and H and H again. And again, that's both of them. So I'm going to go in a little different direction. And rather than designate internal and terminal, considering they both do it, I changed my mind. I'm now going to designate if it only does terminal or only does internal. Next on here, I want to put NaNH3, and this is the one. It only works on an internal. So I'm going to put internal only, meaning it does not work on a terminal alkyne because it'll deprotonate that H. HBr, we know that H goes to less hindered, Br goes to more hindered. Notice the CCl4 solvent in here. I didn't bring up any solvent throughout this whole thing when it came to HBr. It's kind of a carryover from what we do on other ones. It is not important, and I'm actually going to remove it because it can be done in various different solvents. So I'm going to just put an HBr going down. Cl2, that on the other hand, Cr2 and Br2, when you add them, works best in an aprotic solvent and non-polar solvent as well. Okay, so this one, I'm drawing them trans. It does not necessarily have to be trans. It can be syn addition, trans addition. Doesn't necessarily favor one over the other. Your more sterically stable compound will be your major product. We have excess Br2. So this is kind of the same thing here, showing then that just like this reagent can react with both, Cl2 and Br2 can react with both. If I put one equivalent, it stops here. If I put excess, you can easily change the Cl2 here to Cl2 here and the Br2 here to Br2 here. So I really should say halogens in general. So you might want to add that to your chart, that this can be Cl or Br, this can be Cl or Br. So far there's only one that's internal only. R2 beach represents 9-BBN or any other variation where you have a bulky boron species to begin with. So it'll choose to add the O, well, the B initially and the OH to the less hindered, and then that tautomerization. So it's up to you, but you might want to put a little note, tautomers, for that one right there. Next on the agenda, whereas this puts on an anti-Markovnikov, this puts on a Markovnikov. And again, it's not truly Markovnikov because it's a triple bond, not a double bond. But this species will put the carbonyl on the more substituted, so we get methyl ketones. And I want to emphasize that. It's a methyl ketone when you react with a terminal. A couple more to go. If I treat the same reagent with an internal, I'm going to get both species as a double bond to O either side. Could be either one. And then last but not least, going to add the ozonolysis, which cleaves the triple bond, put you there. Again, it can work on both. So there really was only one internal only. I was way too stressed out about that. Now that I have my spider chart, I can trade reactions around. So I put that on both. I put that on both, and if you want to put Lindlar catalyst here and H2 with just PT here and show that this one's there and that one's there, that's fine too. Just make note of just what reactions can go both, like on both a terminal and an internal. So lots of information. This particular video, I think, was just about organizing, putting it all in one space, trying a few sample questions. But that's what OChem is about, and that's definitely what it's going to be about for the remainder of the entire course, not just this semester, but also any future OChem courses you take. It's about processing a lot of reactions, figuring out the nuances of them through the mechanism, knowing what their favoritism is in terms of regioselectivity and stereoselectivity, and then ultimately figuring out how to use them in synthetic pathways to generate an infinite number of compounds. A lot of work on this one. So hopefully this is going well. This ends alkynes. We'll next go into alkane chemistry, but halogenation of alkanes and free radicals. So until the next topic, have an absolutely wonderful time, and thank you for joining in the Toddcast.